Hello guys, welcome to my YouTube channel and I hope you to enjoy. I'm running this channel because ever since I remember I always love teaching and sharing my knowledge to other people and also learning in this process because if you have experience in this situation, if you teach somebody a thing you teach somebody your knowledge, uh, sometimes you find some hidden points in that subject when you're explaining it to the other people. And I always loved teaching and learning in that process. I've been teaching assistant several times in my university, and I'm also going to be another teaching assistant in the fall 2022, and also I'm going to be on a research assistant position this coming fall. And this shows that I love teaching. And also, this is my first reason that I'm running this YouTube channel and starting this journey. The second reason is that I want to improve my English speaking skills. So I think these 2 or 3 reasons would be enough to run this YouTube channel, and I hope to be that would be effective. Okay, in the first presentation or the first video, I want to explain the background of my thesis, of my master's thesis. So some fundamental things about an emerging technology named Reconfigurable Intelligent Surface, or RIS, also known as IRS, which is abbreviation of Intelligent Reflecting Surfaces. So I want to talk about RIS-Assisted wireless communications, which between 3 and 4 years, about 4 years ago, it was first introduced, and even now it is in a widespread manner. Researchers are working on it and do their research also either in theory or the practical situations. So it would be an important technology in the sixth generation of wireless networks. So this is an outline here which I want to talk about in this presentation. At first, introduction, then what is RIS exactly? Is it really necessary in our systems? I explain existing problems, motivations to go to this direction, and comparison to the existing technologies. Also, I talk about challenges and system model in the RIS-assisted wireless communications and systems. Also, problem formulations, applications, notable researchers, practical projects, journals, and at the end, references. So, as an introduction, I should explain very briefly the beamforming subject. What is beamforming and what we do with that? In the fifth generation of wireless networks, it was introduced almost in the fifth generation, which when we have a single antenna, for example, a dipole antenna, it would radiate the signal in 360 degree. It is omnidirectional and spread its signal and waves in all directions. But when we put another antenna next to it, for example, with the distance of lambda divided by 2, which lambda is the wavelength of the signal that is radiated. The The radiated signals would combine with each other. Each of them radiate a signal, a similar signal, and when they are radiated in the same time from these two antennae, it would combine together, and in some directions it would make constructive interference, and in other ways, in other directions, it would make a constructive interference. For example, in this shape, in this image, you can see that in this direction they are in the same phase, the signals which were radiated. They have the same phase, so it is a constructive interference, and we have more powerful signal in this direction. But in these directions, the side directions, the radiated signals are combined together in a destructive manner, and they make themselves neutral. So we have barely signal power in these directions. But in most situations, when we have a main lobe in this direction, we have some side lobes in the sides, and compensating these side lobes needs some new technologies which are now available. We can minimize these side lobe powers with a good amount of power. And also in this image, we have two radiators with different powers. This antenna radiate the signals in less power, and this antenna radiates the signal more powerfully. So the constructive interference would be in this direction. We have a side lobe here and the main lobe here. Actually, vice versa. We have a main lobe here and a side lobe here. So in RRS or RIS, we make use of this technology to reshape our signal. So reconfigurable intelligent surface is a planar surface which consists of several elements. For example, dipole antennas here, which behind of that is a copper backplane, which and behind that, in the third layer, we have a control circuit board which attached to an RIS controller, for example, an FPGA, which sends the information about the phase shift of these dipoles and perform that phase shifting on that elements. So we have a beamforming, as I said, with changing the phase shifts. And also this RIS controller is connected to an access point or base station with a backhaul link. This backhaul link can be either wireless or wired. These elements on RIS can have 4 different performance. They can reflect the signal, the incident signal. They can refract, absorb, or focus. This focus is that beamforming, which by changing the phase shift of the elements, we can focus the signal in a desired direction, desired angle. Also, reflection just reflects the signal, the incident signal, and doesn't absorb or refract from it, just like a mirror. And also for absorption, the incident signal would be disappeared after the incidence. So The most important part is that focusing. We do the focusing with IRS, the incident signal from the base station on the IRS, with performing the phase shift change, with focus or beamform the incident wave to a desired angle, for example, where a user is. So is it really necessary to implement this technology on our new systems and the future generation of wireless networks? We see. For beyond 5G, we need some new improvements in the wireless networks. The first one is ultra-high data rate, energy efficiency, global coverage and connectivity, extremely high reliability, and extremely low latency. But there are some limitations nowadays without IRS. For deploying increasingly more active nodes to shorten the communication distance for achieving enhanced network coverage and capacity, we need energy, we need cost, and also this would cause some interference in our system. Another limitation is packing substantially more antennas at the base station or access points, or also relays to harness the enormous massive MIMO gains. We need another cost and also complexity. And the third limitation would be migrating to higher frequency bands such as millimeter wave and even terahertz frequencies to utilize their large and available bandwidths. We need more active nodes and more antennas. So energy, cost, interference, complexity, more active nodes, more antennas would be all have extra cost for our systems to reach quite these requirements for going to beyond 5G and have much more better performances in our networks. Also, for this third limitation, as you know, when we go upper in the frequency range, the signals would be more vulnerable to environmental problems such as, for example, rain, wind, and this kind of things. So we need to make the cells smaller and smaller. So the waves would arrive at the destinations in a healthy way and completely and without error. So we need to for more cells, we need more active nodes and more antennas. So what's new in reconfigurable intelligent surfaces? In this image, you can see a network without IRS and network with IRS, which are implemented on buildings and are cooperating with the base stations in the system. In IRS, we have flexible, smart, reconfigurable reflection and beamforming. We can change the CSI, you can change the channel information that phase shift on the IRS, so they are smart and reconfigurable. And also make the network flexible with that. Need substantially less antennas at the base station, reduced hardware cost and energy consumption, so it is energy efficient and also reduces the costs. Base station beamforming and IRS phase shift joint optimization. I talk about that later, which in the for example 5th generation we didn't have joint optimization. We only optimized, for example, one variable, which was base station beamforming or pre-coding vector at the base station. But here we have IRS phase shift to be optimized. So this joint optimization, which in most cases is IRS phase shift and base station beamforming, vector are coupled, so this joint optimization would be so hard to be solved exactly and without approximations. Also, it covers dead zones. For example, if this building exists here and the user exists here at the back of the building and base station is here, so the SNR, the signal SNR which is received at the user is so low, and maybe the connection wouldn't be created. So if an IRS exists here, a base station can send the signal to the IRS, and IRS can be optimized to reflect this incident signal from the base station to the user. So two line of sight path, and the SNR which receives the user would be so high and the connection would be so strong. Coverage extension in millimeter wave and terrestrial communication, so we don't need more antennas and more nodes in the network. Improve the desired signal power at cell edge users. Suppression of co-channel interference from neighboring cells. Compensation of power loss over long distances. Enhanced communications in indoor and outdoor environment. It can be both utilized in indoor and outdoor environment. And also improving physical layer security. But it has minor problems which we can ignore them. They're not that important, but I should explain them. Reflected signal coupling. We don't consider the signal coupling and the elements of the IRS in the research. Also, no frequency selective elements. The elements of the IRS, they are not frequency selective and cannot support two different frequency ranges at the same time, so they're not frequency selective. IRS hardware imperfections. We generally don't assume and don't consider the IRS hardware imperfections in the research, but there are some research that are investigated this phenomenon, and the result says that it's not that important. Alternating phase shifts. Phase shifts can be changing when it is intended to be constant. So this is a problem. TDD channel on reciprocity. In the recent technologies, before introducing IRS, we considered channels, uplink channels, and the downlink channels to be reciprocate. So it would be the same. Uplink and downlink channel would be the same. But with IRS, it is a bit different, and this approximation is more careless. So, but in some researchers, it is proved that it's not that important again. And insensitivity to incident angle. So there are some problems which are not that important. Discrete reflection, amplitude, and phase shift. An element of the IRS would be, for example, in this shape, which has a pin diode and probably more pin diodes, depending on the situation. It can be proved that the level of the phase shift, for example, phase shift, we have 0 to 180, okay? In many researches, it is assumed that the phase shifts are continuous. But in the practical situation, when we want a continuous phase shift, for example, we want the phase shift to be 2 degrees, for example. We want 49 degrees. We want 150 degrees. In most researchers, it is considered that it would be it would be possible. But in the practical situation, when we want continuous phase shift change, we should have infinite pin diodes for that to be possible, because the level of the phase shift, if we take a log from it, it would be the number of pin diodes that is needed. For example, we want 8 phase shift from 0 to 180, just 8 phase shift. So we want 3 pin diodes on each element of the RIS. For example, if the RIS has 64 elements and each element has 3 pin diodes, it would be several pin diodes to be used. So it is not practical it isn't practical to assume continuous phase shift on the elements of the IRS. But it is proved that when we use a 1-bit phase shift, for example, it means that 2 phase shift, okay? The SNR would be such that as the elements of the IRS increases. And when we have 2-bit phase control, it means that we have four phase shifts. The result would be almost the same as the situation when we assume we have a continuous phase shift. The SNR doesn't differ that much. So it is good. It is a good news for us. And the performance would be so good with just 4 phase shifts. So what's the difference between IRS and relay? Relay, as you know, receives a signal from the, for example, base station in long distances, and for improving the SNR, which will be received by the user, receives a signal from the base station and do some processing and amplification on the signal and retransmit it again to the user. So the SNR which is received at the user would be high and enough. But IRS differs in some ways. IRS doesn't do the processing on the signal because it doesn't have RF chains, and just reflects the signal and doesn't use energy at all, except for the microcontroller to be working. And except that it doesn't use energy, so it would be so much more energy efficient than the relay. But the signal processing complexity would be higher than the signal complexity which is needed for the processing of relay-assisted networks. So IRS is more energy efficient. Energy consumption, RF chain doesn't have RF chain, but relays have RF chains. IRS is full duplex. A relay in most cases are half duplex, and it is more logical to be half duplex in relay. So IRS would have spectral efficiency because it is full duplex. IRS doesn't have antenna, so it doesn't have antenna noise. It doesn't cause interference. More spectral efficient. Less cost, profile, and weight. It is more easier to work with. Better geometry and flexibility and compatibility. In this research, it is proved that when we use a half duplex decode and forward relay, full duplex decode and forward relay, full duplex decode and forward, the ideal situation, and RIS. And it is proven and it is shown that the rate compared with frequency for the IRS, which is the black one, and the full duplex decoding forward, the ideal situation, which is the green one, is almost the same. And in this situation, when the distance is 100 meters, in some situation, in some frequency ranges, the RIS has better performance, even better performance. So RIS is so promising to be used in the future technologies, but it has some challenges. The first one, it is reflection optimization. As I said, in the previous technologies, we had just the pre-coding vector at the base station to be optimized, but in this situation, the IRS phase shifts also needed to be optimized. So we have a joint optimization, which are actually coupled. The two parameters and unknown variables are coupled, and this joint optimization would be so hard to be solved. If we have non-convex optimization in that journey, we have NP-hard problems. And so cooperative signal focusing and or interference cancellation in RS local proximity, jointly designed with the base stations or users transmission, end-to-end communication optimization. We have a joint optimization here, and it is common that would be non-convex problem or NP-hard problem. So this is a difficult task, and tons of actually researchers are in this topic, reflection optimization. The second challenge is the channel estimation. As IRS doesn't have RF chains, so it doesn't have the signal processing unit, so the channel estimation is not the same as before, because in the typical situation in previous technologies, base station or user send pilot signals to the other side, and the other side, which knows the pilot signals previously, does the channel estimation with, for example, least squares or MMSE techniques. These techniques to do the channel estimation, and it's not that difficult. And they are new technologies, new methods and algorithms to reduce the error of the channel estimation. But in the IRS assisted wireless networks, as IRS is between the base station and the user. For example, base station sends the signal to the IRS, and IRS reflects it to the user. So we have two channels here: base station to IRS channel and IRS to user channel. And between them, the phase shift of the IRS affect the channels. So the channel would be the base station IRS channel multiplied by the diagonal form of the IRS phase shift multiplied by this channel between user and IRS. As we don't know the phase shift of the IRS, which are needed to be optimized later, this channel is unknown, because we have another unknown variable, which is phase shift of the IRS in that. So these LS and MMSE techniques are no longer useful here, and we should do something about it. Channel estimation is a very difficult task in IRS assisted wireless communications, and again, several researchers have worked on this topic. And very innovative channels has introduced here. So this is another challenge. Channel estimation is essential to the IRS reflection optimization, a difficult task, especially with a large number of reflecting elements. And the third challenge would be the optimal deployment strategy of IRSs for maximizing the network capacity. This would result in passive and reflecting structures of IRS versus active and transmit receive. Makes it difficult. Deployment of the IRS to maximize the network would be another optimization, which is not that important compared with the first and the second challenge. So we talk about these first two challenges in the next slides. First, the system model in the RIS-assisted networks. In these figures, figure 9 and figure 10. In figure 10, we have a single user system, and in the figure 10, we have multi-user system. As I said, the direct channel, which is assumed to be so weak, for example, some obstacles in the way, and the focus of us is on that channel, G multiplied by the diagonal form of the elements, phase shift of the elements of the IRS, multiplied by HR Hermitian. So, as I said, that is a difficult task due to we don't know the IRS elements, phase shift of the elements. We assume that it is a single channel, not the multiplication of the two channels. We call this channel diagonal form of HR Hermitian multiplied by G, the cascaded channel. It is called the cascaded channel, and we intend to estimate this channel instead of estimation of the separate channels. So YK, the signal which is received at the base station from K users, would be HRK Hermitian, phi, which is the diagonal form of the phase shift of the IRS, multiplied by G. Okay, this channel here is here, and HDK Hermitian, which is this channel, the sum of these two channels would be the effective channel, and multiplied by signals. Actually, this is a transmitting signal from the base station to the K users. SJ is the original signal to be transmitted, and WJ is the pre-coding vector at the base station to, for example, reduce interference and quality of service things, and is here. And it is multiplied to the original signal to reduce, for example, as I said, the interference or these things. The sum of them plus a noise which is between nodes, which is generally assumed to be complex Gaussian. So the unknown parameters which needed to be optimized, it is phi, diagonal form of the phase shifts, and also this WJ, which is a pre-coding vector at the base station. As an example, signal to interference plus noise for user K would be the original signal, this channel, multiplied by WKSK, which K is the intended user, the desired user, and here it is assumed that the power of the original signal is 1. This is a unit, has unit power. divided by the interference plus noise. This is the noise term, this is the variance of the noise, and this term is the interference caused by other users. And here it is the cascaded channel which I said, G multiplied by diagonal form of the HRK Hermitian. Here we can change it. Phi is the diagonal of, for example, theta. We can take out the theta here and take HRK into the diagonal function. So it would be theta, diagonal form of HRK multiplied by G. So this channel would be the effective channel. Effective channel is here. And as IRS doesn't have, as I said, it is energy efficient and doesn't use energy, we assume that the beta n, which is the amplification of the signal, the incident signal on the IRS, we assume that it is 0 or 1. 0 or 1, which means that it doesn't amplify the signal, it just reflects it. And theta would be between 0 and 2 pi. It is a complex, it is the continuous form, and it can be assumed to be discrete. Past law models of IRS reflected channels. We know that pass loss is related to the inverse of the distances. For example, transmitter distance from transmitter to this element and this element to the receiver. The pass loss has inverse effect compared to these distances. So when we use an IRS, the distance compared to the direct distance would be more, so the pass loss would be increased. But there is a special property in RIS-assisted networks, which is receive power scaling with n. If we have this system model here, it is proved that instead of n, which is the elements of the IRS or antennas at the antennas on the relays. Example, on the relays, if we had n antennas, the received power at the destination would multiply it by n. But it is proven that in RIS-assisted networks, the power is multiplied by n to the power of 2. So we have extra power here. So this pass loss here would be compensated here, and we also have higher SNRs here. This n to the power of 2, one n is for reflect beamforming gain, and the other is additional aperture gain of IRS. In this figure also we can see that comparing 200 elements and 400 elements, this formula is satisfied. Common assumption in the researches in RS topic. Channel state information, some consider perfect CSI and do the optimizations, joint optimization that I said, and some assume unknown CSI, which they intend to do the channel estimation. Phase shift, some assume discrete phase shift and some assume continuous phase shift, which the discrete one is more practical. Energy consumption, some assume all elements are passive and doesn't have RF chain and signal processing gain, and therefore they don't use energy. And some assume hybrid IRS, which contains some elements to be passive and some elements to be active. For example, 5% or 10% of the elements would be active here, and they have RF chain and do the signal processing, but it is not that practical because it uses so much energy, and the IRS wouldn't be energy efficient anymore. Some assume single antenna, multi-antenna, single cell, multi-cell. In the frequency band, some assume millimeter wave, terahertz, and also they assume narrowband signal, broadband signal, which broadband signal causes some difficulties in IRS technologies. And some assume single user and multi-user networks. There are some common optimization and decision-making techniques in IRS and the joint optimization. Problems, which are the simplest ones, are gradient descent and genetic algorithm, which are not that much practical and useful. For example, that absolute of theta was the phase shift of the IRS. Absolute of the theta equals 1, okay, 1, because I said that as IRS doesn't do the amplification, we assume that the amplification coefficient would be 1, okay? It means that it just reflects the incident signal. So one of the constraints in the optimization problems are absolute of each of the phase shift, okay, I mean the magnitude, equals 1. But it is a non-convex. This is a non-convex constraint which is called unit modulus constraint. And with SDR, or semi-definite relaxation, we can relax this constraint and transform it to a convex optimization constraint. Convex constraint, and it can be solved with, for example, CVX tool in MATLAB. Also, as I said, we face joint optimization, which by this being couple of these parameters, pre-coding vector at the base station and the phase shift of the IRS, as they are coupled in the optimization, we use alternating optimization to which assumes one of the parameters fixed and one of the parameters is variable. So do the optimization on that variable, and in the next iteration it will assume that the variable in the previous step is fixed and the other variable is can be optimized. So it would repeat this process until the result of the optimization of the two parameters converge to a constant value. Another optimization technique is fractional programming. Also, we have exhaustive search, which is not efficient and it is used to find the optimal answer and compare our results with the ideal answer. ADMM, or branch unbound, and also we use data-driven, such as ML techniques, deep learning. For example, for channel estimation, we can use deep learning. Deep reinforcement learning, federated learning, multi-layer perceptron. For example, for deep reinforcement learning, we can optimize these joint optimization problems without this alternating optimization. It solved the problem simultaneously for both variables. So this would be efficient and has less complexity. Some problem formulation. Some researchers are assumed perfect CSI in their research, and some assume unknown CSI, which these group do the optimization problems, and these group do the channel estimation, which both are difficult tasks in IRS assisted networks. For perfect CSI, they do the energy efficiency optimizations, SINR maximization, rate maximization, and also security enhancement, which I've brought some examples with links here, which if you click on it, the papers would be shown. And also, I upload these presentation so you can use that. Also, by clicking on these links, the papers will be shown. And for channel estimation, we have cascaded channel estimation methods, on-off method, which is the simplest and the most basic approach for channel estimation. Discrete Fourier transform, protocol-based, sparse channel matrix recovery, deep denoising convolutional network, neural network, or DNCNN, generative adversarial network, or GAN, deep learning, compressed sensing, element grouping, convolutional neural network, or CNN, which again has links and you can read the papers. Other research areas which can combine to the IRS would be, for example, UAV, NOMA, terahertz communication, SWIFT, cell-free networks, localization, seascape, vehicular networks, and IoT networks. In UAV assisted, you can see this UAV carrying an IRS to help the system. NOMA communications, physical layer security, millimeter wave communication, and SWIFT. We have some notable researchers here. Practical projects. This is a practical project in England, in University of Surrey. This is a practical project in China, which shows that in outdoor environment with a distance of 50 meters, the existing of IRS would help the system to increase the SNR. And this project is again in China, but with a distance of 500 meters. And also with IRS, we can see that the received SNR is increased. Some journals and conferences, references, and thanks for your time and attention.